Recording here. Yes, ma'am.
You said that you would post schedule of our exams and chapters over Expert TA. I can't seem to find it.
Yeah, I haven't done that because I've been lazy. Let's take a look at that really quick here. Let's get into Expert TA and figure out how I can do a schedule in there. Excuse me. Why is this not working? Okay. Please to the roster. They don't really have a calendar in this thing, do they? Just this list of assignments. Okay, we'll do it that way. Let's create, let's see. Let's create an assignment. Excuse me. Okay, so exam 1 will be covering 18, 19, 20, and 21. And then a second exam would cover 22, 23, 24, 25, and 26, and 20. So 22 through 27 would be like 6 chapters, but it's be the first 4 chapters and then the next 6 chapters. And then the final will cover everything else. So today we start chapter 20. Next week we start chapter 21. And so it would be 2 weeks from now. Today is the 31st. And then we have the 7th. So it would be the week of, what's wrong with my calendar? Week of the 14th anyway. So 14th, 15th, 16th, 17th probably is when it would be due. This assignment will be exam, and we'll call it exam 18 through 21, because we'll cover those chapters. Exam 18 through 21. This will be a midterm. And the grading template will be that, we'll call it that. We'll worry about the problems that we're putting in it later. But we will make it due the 17th of February. It will be a timed assignment for probably 2 hours. Maybe we give you 3 hours. And then I have to still figure out how to put it so that it's a password protected thing. I don't know how to do that. Oh, security down here. I'll do that later. So I will save this and exit it. So now, save only. Okay. So now it should be in our schedule. Let's go see. Dang it, it's not in the schedule. I have to select a problem apparently. Let's try that again. Please select create assignment. Exam 18 through 21. Midterm 217. 217. We should probably make that a reasonable time. I believe the Success Center closes these days at like on Fridays at 5 or 6 p.m. We'll make it 5 just to be safe. 5 p.m. Timed assignment 180. And we will do, let's see. And we're doing not chapter 1, but chapter 18. We'll just put in a problem randomly just so that it has a problem in it. And we will save. There we go. So now exam 18 through 21 has something. We'll put some security in it. Example IP filter and password. So I can do IP addresses and filters. And passwords. Anyway. Password. I'll do it later. So anyway, that's set up now. Has a date. And the way that will work is that the week after we finish that last chapter, you can take that test anytime you want during that week till Friday. You can take it with me in here, make an appointment with me and take it in here, or you can take it in the Success Center. Either way works fine. You can use your own computer, and you can use your book, online book. I ask you to not use any online resources besides that. If you get caught, they will report you to me, and then the wrath of Jared comes down upon you like a bolt of lightning. But anyway. Okay, so that is our first test in a couple weeks here. We are moving on to chapter 20. We're going to move into a more practical. We started learning about capacitors, which are quite practical. Now we're going to move into electric current resistance and Ohm's law, which is continuing in that vein of practical thinking when it comes to electronics and electrical stuff. And the reason I say practical is because for the most part, in most situations, we're not dealing with electric fields, electric potentials every day, even though they are there. we're mostly dealing with electronics. And electronics have to do with the travel of electrons through circuits, through conductive wires, and conductive and semiconductive and even non-conductive components that are connected to those wires. And it may seem kind of funny that they have this picture of this hydroelectric dam, essentially. This water falling down this big ramp and hitting this thing and spraying out over all. It's kind of a cool picture. But it may seem weird to have this picture in here for this chapter being electric current, resistance, and Ohm's law. Right? What has this got to do with electric current, resistance, and Ohm's law? Well, when we're dealing with electric current, we're going to be dealing with voltage, which we call potential difference, right? Which we already know is related to potential energy. So the potential energy for electrons, what does that mean? To make sense of potential energy for electrons, or potential and potential in electrical situations, we use the analogy of potential energy in gravity. So you have water at the top of this dam, and it has the potential energy to fall down, and so it does fall down. And then it goes off this ramp and it flies up into the air again, and it gains potential again, potential energy again, and then it falls down again, right? And while it's falling down, it gains kinetic energy. You can look at this in a very traditional and mechanical way. But we can also imagine this as like electrons. When electrons, or charges of any kind, really, are at a high potential, that means they have a lot of ability to become energetic, to gain energy. And when we're talking about these things, we talk about current. So we have current in a circuit, and at different places in the circuit, that current has different potentials, or that circuit has different potentials. And at the places where the circuit has a high potential difference between 2 points, that means that the current has a much higher ability, or a much higher potential to go through the circuit, or to move through the circuit. And you could think that as the current moves through the circuit from a high potential to a low potential, it's kind of like the water going from a high potential energy to a low potential energy. The current gains a lot of energy as it goes through a big potential in a circuit. And so we're going to use that analogy quite a bit, and that's why they use this. And also, they have this dam in here because dams like this produce electricity, which is also helpful. It turns out that electric potentials and electric currents are everywhere. And not just in electronics. I mean, they're everywhere. They're everywhere in our atmosphere. They're everywhere around us in many, many ways. They're inside of our bodies, inside of our brains. Everything that we think and do is caused and driven by electrical currents and potentials. So it's an important thing for us to understand. Let's start with a definition. What is current anyway? Electrical current is defined as an amount of charge passing through a given area in a given time. So mathematically, we say there's some amount of charge in some amount that goes by in some amount of time. We don't explicitly talk about the area in this equation here, but it is implied that that charge is passing some point in air, through some cross-sectional area, you could think of it like a window. But that charge is passing through something, through some area, in some given amount of time, delta t. And this unit, or this amount of stuff passing through in this amount of time, is given the unit of amps. It's coulombs per second, because charge is coulombs, time is seconds. And coulombs per second is named amps, or amperes, named after a famous scientist, of course, a famous physicist, named Ampere. And this is a nice representation of, a nice kind of visual representation of how this goes. we have charges, and notice that they're just calling them Q. They're not calling them electrons. They're not calling them anything, really. They're just calling them Q. And these charges are going to flow through this cross-sectional area, A, this little circle here, in some kind of in some given rate or given amount of time. The charge that passes for current to be a positive current has to be a positive charge. Notice that Q over T doesn't have any signs in it. So it has to be the passage of positive charge. And that's going to confuse the heck out of us because we've already decided that it's the electron that moves, not the proton, just because we know some things about matter and we know some things about atoms. And so how can we talk about the protons moving? The protons aren't really moving. The electrons are moving. But because of our friend Benjamin Franklin, a few hundred years ago, because he decided that he was going to make the electron the negative charge, everything turns out backwards. He should have made the electron the positive charge, then we wouldn't have to worry about this. But he didn't, and we've stuck with that decision ever since. Stupid people that we are in this world. We should have just turned over his decision and changed it, but we didn't. And so we have to think of charge as the flow, we have to think of current as the flow of positive charge, even though the negative charges are the things that are moving. So whichever direction the electrons are moving through a wire, the current is in the other direction. It's as if the protons would be moving in the other direction. Confusing? Yes. Obnoxious? Yes. Will it mess you up? Absolutely. But you'll eventually get used to it. You'll eventually get used to being confused by this, and you'll just accept it like everyone else of us, all the rest of us sheep in the electrical world. We just follow the herd, follow the flock, right? So, let's do a simple problem with this very simple definition. We have 720 coulombs of charge being moved by a battery in 4 seconds through some area, probably the area in the cross section of the wire or whatever. And this is happening while it's starting the engine. We want to know how long it takes 1 coulomb of charge to flow through a handheld calculator. Oh, we also want to know how long it takes this is a separate problem. 1 coulomb of charge to flow through a handheld calculator, there's 0.3 milliamps of current flowing in the calculator. So we start with the first one. The first one, they give us the amount of charge and the time, which is simple. Charge divided by time is equal to current. So we get 720 divided by 400, we get 180 coulombs per second. That's 180 amps. In case you're wondering, that's a lot of current. Okay? 180 amps will kill any living organism if it has enough voltage to travel to get through its skin or whatever. 180 amps is a lot of current, and it's current that kills things. Just in case you're wondering, current cooks. Current is the thing that dissipates heat in things, and it cooks things. 180 amps is more than enough to cook some. In fact, 15 amps, I can cook a hot dog with 15 amps out of the wall socket pretty easily. I mean, it takes about 10 seconds to cook the hot dog. So it's a lot of current, 180 amps. Just there's not much voltage because it's only 12 volts, and 12 volts won't go through your skin unless your skin is wet. So that's right. The voltage is not the thing that kills you, but the voltage is the thing that allows the current to kill you. So if you don't have a high enough voltage, it can't get through your skin, so it can't drive that current through your body very easily. Voltage is the thing that drives the current, that pushes the current through things. And some things are easier to push current through than others. For example, the water inside of your body has lots of salt in it, and that salt is a really good conductor. Water itself is not a very good conductor, just pure water. But water with things in it, very good conductor, it turns out, because usually there are salts, and salts make great conductors. So if you get past the skin, which has very little water in it, then you're in real danger with that much current. But it takes probably 30 to 40, 50 volts to get through dry skin in your hands. If your hands are wet with oil or water, then you're in trouble because then very little voltage you can get through your skin, wet skin, with 2 or 3 volts. So, and that's a very important thing that we will talk about quite a bit. What is the difference between voltage and current? Well, it's the same thing as the difference between water flow and the height that water is falling from. Does it matter how much water you have? If you're dropping it from 20 feet, can a cup fall from 20 feet just as much as a gallon? Sure. You can have a cup fall from 20 feet and a gallon fall from 20 feet. And a cup of water will make you wet, but not very wet. A gallon of water will make you very wet, right? It's the difference between a water balloon this size, a little tiny one, and a water balloon this size, right? And so the current is the amount of water. That's how wet you're going to get. The height is how much it's going to hurt when it hits you, right? So 180 amps at 12 volts, it may not hurt you very much, but it'll still cook you. It's going to cook your body. And it may not do it very quickly, but it'll still do it. Whereas if you had 180 amps at 180 volts, it's both going to hurt and cook you, and it's going to do it quickly. So it has something to do with the time it takes for damage to occur. Because that current is going to be driven through you quicker with more energy, the more voltage there is. So that's a couple of different ways to think about this. 180 amps battery, that's not uncommon. In fact, many batteries can crank a lot more than that. I think my battery on my car will do, I want to say it'll do 600 amps or something like that. I can't remember exactly what it is, but it's fair enough. Anyway, so here is the next one. The next one is they're giving us the amount of current, which is 0.3 milliamps? Where did we go here? Yeah, 0.3 milliamps. So that's 0.3 times 10 to the minus 3 amps, right? So that's right there, 0.3 times. So they've rearranged the equation, you can see, to solve for delta T instead of to solve for amps, because they've given us the current. So we got 0.3 times 10 to the minus 3 coulombs per second, or amps. And then we have 1 coulomb of charge that we want to see how long it takes for it to go through. When you solve this, it turns out to be 3.33 times 10 to the 3 seconds. So that's 3,000 seconds. What's 3,000 seconds? It's like an hour, right? 3,600 seconds is an hour. 3,330, 303, whatever. 330 seconds is almost an hour. But it's a long time. A calculator, if you used it constantly for an hour, would eventually use up 1 coulomb of charge, but it doesn't use that much. In fact, many calculators use much less anymore these days. And this is actually a huge deal because the amount of charge that you use up is the amount of battery that you use up, in essence, right? So your battery can only hold so much charge, and it can only store so much charge, and once you've used it up, the battery's dead. So they're constantly trying to get this number, this time that it takes to use up that charge higher and higher and higher. They want that amount of time that you can use your laptop or your cell phone to be longer and longer and longer and longer. You can do that a lot of different ways. You can do it by getting better batteries, but that's a difficult thing to do. That's kind of restricted by the chemicals and the size of the battery. Or you can change the electronics so that the electronics take up less battery, use less power. So this is why your cell phone, for example, has all kinds of features that shut things down when you're not using them, that make things sleep, that dim the screen. All kinds of things are built into your cell phone to make it so that it uses less and less battery. Because cell phones, especially these smartphones with their big bright screens, that screen uses more battery than anything on that whole phone. Important. So let's talk a little bit about circuits for a second. Why do we call it a circuit? Can anyone guess? Don't even know what the word circuit means.
You get connects to both sides.
Okay? Yeah, the circuit literally means circle, right? A circuit is something that goes in a circle. So when you have a circuit in sports, usually that means there are a bunch of sites or a bunch of tournaments, and you go around and around these tournaments until you've done the entire circuit, and then you start over again the next season or the next year or whatever. So that's in sports. They have a circuit, or they often call racetracks circuits. So you have a racetrack that's a circuit because it goes all the way around, does whatever it's going to do, then it comes back to the same point, and then you start again. You keep going around. Right? And circuits in electronics are the same thing. A circuit is a circle. And the circle is made by wires, which are represented by lines. Resistors are one of the components that are in circuits, so there are other components like capacitors. So it's made of wires and components and power sources, which are like batteries or power supplies or other things. And you can also have meters in your circuit, meters for measuring things, which we haven't put in there yet. So this is a physical circuit. We have a battery with two leads on it, a positive lead and a negative lead. The positive tells us which side is the high potential of the battery. So the positive side of the battery is where high potential is. The negative side is where low potential is. And current will always flow from high potential to low potential in a circuit. Okay, so if we connect this battery to a headlight in a car, we connect it, and a headlight is essentially just a resistor that glows when it gets hot. So it's got this resistor. If we connect the battery to it, it's like connecting the positive side or the high potential side to one side of the resistor, and the negative side or the low side of the battery, low potential side of the battery, to the other side of the resistor. And that will cause current to want to flow through that resistor from the high side to the low side of the battery. You can see that the current is represented by the blue arrows here. Which way are the electrons moving? Clockwise or counterclockwise? This is the quiz of the day. You have a piece of paper out. Put your name on it, date on it. Put your name on it, put your date on it, and tell me, draw a picture of the circuit too, with the battery and the resistor in it. I would like to see a picture of that circuit so that I can remember what the circuit was in the quiz. And your question for today is, so you're going to draw the circuit with the direction of the current and everything, and you're going to tell me which way the electrons are moving, clockwise or counterclockwise, with that drawing of that circuit in the quiz. Okay, anybody need more time? If you're done, I'll take your quiz. Is this the label for the current or the electrons? Okay, show me the direction of the current and show me the direction of your electrons. I want to see the direction of the current and the electrons so that I can tell which, and you can either write it or label it both ways. What's that? Current is just labeled with the letter I, by the way. We use I for capital I for current. Thank you. Okay, so you all give an answer. Does everybody want to share their answer? The current is moving clockwise. Which direction are the electrons moving? We have a vote for counterclockwise. Anybody agree or disagree? We have a disagree at clockwise. Anybody else want to weigh in? We have one each. Clockwise or counterclockwise? Well, let's go back to our definition. Our definition says that current is the flow of Q over T. Delta Q over delta T, right? There are no signs in this. So the current, if it's going to be positive current, which it is in circuits, we always consider current to be positive. If it's going to be positive, then that Q has to be positive because time is always positive, right? So current is the flow of positive charge from this. And do positive charges actually move? Not usually, because usually it's electrons that move. So if current is the flow of positive charge, which direction do the electrons flow if our current is going clockwise? Because current is the flow of positive charges. That would be the flow if the positive charges did move. The electrons would flow in the opposite direction, right? Counterclockwise. So it's counterclockwise if the current flows clockwise in a wire, in a circuit. The only exceptions to this are when currents flow in a situation where positive charges can actually flow. Positive charges can flow in situations like in liquids, but not in metals. In metals, only electrons move. We learned about that in our last chapter, or chapter before that, first chapter, when we learned about conductors. So current is always the flow of, current is always the flow in circuits like, wires and things like this. There's always the flow of positive charge, quote unquote, but the things that actually move are the electrons. Who do we have to thank for that? Benjamin Franklin. What a dork. He couldn't have possibly known. Back then, the things that he did were quite brilliant, considering what he had to work with. This is kind of what it looks like in a conductor. In the top one, this is what we imagine. This is what Benjamin Franklin imagined was happening, where you have positive charges flowing in the direction of the current. Positive charges moving along through the wire. But since we know that positive charges are connected to the actual atoms of the wire, and the atoms of the wire aren't the thing moving, then we have to assume that this is actually what's happening, that the current is flowing in the right-hand direction, but what's actually happening is the electrons are moving in the opposite direction. It's kind of like pulling into a parking slot. You know when you're pulling into a parking slot, and then the car next to you starts pulling out, and you feel like you're still moving forward? It's that same effect. The electrons going one way is the same idea as the positive charges going the other way. It has the same effect. So it doesn't really matter. The interesting thing here is that there is an electric field that is causing this to happen. And that electric field is in the direction of the current. It's in the electric field in a circuit always goes from high potential to low potential, just like it does in any other situation with potential. If you have a high potential and a low potential somewhere out in space, the electric field will always point from the high potential towards the low potential. And will cross equipotential lines at perpendicular angles, just like you learned in your lab. So the electric field is the thing that's causing this causing these charges to move through the conductor, to get an electric field inside of that conductor. So let's take a look at this example where we have that 0.300 milliamp current traveling through the calculator like the other example. And we want to know how many electrons per second are passing through this. Well, remember that the current is equal to a charge over time. And the number of electrons moving is the same as the number of positive charges that would be moving if they were moving. So it ends up being 0.3 times 10 to the minus 3 coulombs per second of electrons. Well, how many electrons is that? Well, coulombs, remember, there are negative 1.6 times 10 to the minus 19 coulombs per electron. So we're just going to convert this current into electrons per second instead of coulombs per second. We do that by dividing by the negative 1.6 times 10 to the minus 19 coulombs. And we end up with 1.88 times 10 to the 15 electrons per second. It's a lot of electrons for such a small current, right? It's a huge amount of electrons. Now, as electrons move through conductors, it's often assumed that they have some kind of speed that is standard, for a certain voltage they go a certain speed, which is kind of true. It's a little bit true, but it's what we call, it's an average velocity. It's what we call a root mean squared velocity, because not all of the electrons are moving in the same direction, not all of them are moving the same speed. There's a lot of different things, and they don't move from one point to another necessarily. So the electron, if you start your car, for example, you're starting your car, and the electrons start out in the battery, and as soon as you start the car, those electrons move towards the starter and turn the starter. But the electrons that were in the battery may never ever get to the starter motor. They may never get there. What really happens is those electrons in the battery start to move, and then they push other electrons, and those electrons push other electrons, and those push. It's kind of like dominoes. It's a domino effect kind of thing, where the electrons that started the dominoes that started the effect don't move very far, but they cause a very, very quick movement and a very, very long movement across a long distance. Okay? This is a great thing for electricity because it allows electricity to move extremely quickly. Electricity can move almost the speed of light in many situations because of this domino effect. They push each other, and this happens. This happens extremely quickly. So the electrons themselves may not move that far, and you actually get what is called a drift velocity for the electrons. So here's an example of what an electron might do. It might move this far and then hit another electron and bounce, and then move this far and then hit another electron and bounce, and then move this far, and then it may move completely backwards. And then it moves along, and eventually it moves from one point to another, but it doesn't move very far. And it has this drift velocity, we call it, as it tries to move forward through the wire, which is not as fast as people would think it is. But it can still be pretty fast. As a result, though, with all these collisions and all this moving around, you do get heat. Electrical currents cause heat, and that's one of the downsides to electricity, or the upsides to electricity. When you're dealing with things like a calculator, one of the reasons that we lose energy with a calculator and burn our batteries is because it creates heat. And we lose that heat. That heat radiates out from the calculator. This is your battery. I found it just spare the heat radiates outward, and you lose that heat, and it's just lost. And then the battery loses that energy and eventually has to be recharged. It's the same with cars. It's the same with everything. Most of the energy that we lose in electricity is due to heat losses. Even if you go out to the wires hanging above the streets outside, most of the energy lost in those wires is heat to their surroundings. You very rarely see ice hanging off of wires. You have to have a serious ice storm to get those things, to get enough ice on those things so so they're not melting. Because they stay pretty warm. We're one of the few places in the United States that get an ice storm bad enough that you can actually get an ice hanging off them. We don't even get them that often. Heat is one of the big things that is caused by electricity. Why can this be a good thing? Well, it turns out that if you make a heater with electricity, it's the only kind of heater that you can make that is 100% efficient. All of the energy that you put in to electricity either goes through the wire and comes back out the other side and doesn't get lost, or it gets lost due to heat, unless it starts to glow and gets lost in the form of light. So you can make a heater if it doesn't glow, if it's just a heater that stays the color of the wire, you can make a heater that is 100% efficient. All of the heat that comes off of it, all of the energy that's lost in the wire is lost in the form of heat and just heats up your house. So why don't we use it if it's 100% efficient? Because electricity is more expensive than gas. So it's actually more economically efficient to just waste some gas and waste some energy and use gas to heat your house instead of electricity. Eventually, that may not be the case. Eventually, it may be cheaper to use electricity than to use gas to heat our houses. Someday. Okay, so now let's take a look at a different way to think about current. Let's look at a way that is more physical. So here's our wire. We have the charges in the wire. These are positive charges. We're back to pretending that positive charges move through the wire in our current. So we have our current that's moving to the right. We have this drift velocity of our charges to the right. We have this cross-sectional area that we've cut out of the wire so that we know which area the charge is going to pass through as we count the charges going through in some amount of time. But how are we going to actually count them? It's not going to be easy to just sit there and go 1, 2, 3, 4, 5 because it's like, gazillions, 10 to the 15 or 10 to the 30 or some huge number of charges. Won't be 10 to the 30, that would be a huge current. But most currents are in the 10 to the 15 range to 10 to the 17 range. Most currents are pretty big currents, could be as much as 10 to the 18, 19 range. So lots and lots of charges. We're not going to be able to just count them. So what we do is we start to think in terms of how many charges are in this volume of the wire. So we're going to take a length of the wire times this area, which will give us a volume. And the length is going to be determined by the velocity of the charges times the time that they pass through. So it's going to be our drift velocity times time will be this distance x. So it'll be x times area, which will give us a volume of wire, which will contain a certain amount of charge. That certain amount of charge, if we take the area times that distance, that's that volume. Then we multiply by the number of charges that are in that volume. And then we multiply by the value that each charge has, Q, which is 1.6 times 10 to the minus 19 coulombs per charge. So this now becomes our charge. And this is now charge per time. Right? But we have now x over delta t, a distance divided by a time, which is actually our drift velocity. So now we can change that equation to current equals the number of charges passing through times the elementary charge times the cross-sectional area of the wire times the drift velocity of the particles. Well, why would we do this? Because this will allow us to calculate the drift velocity. So now we can rearrange that equation and calculate the drift velocity of the particles. So they want us to do that here. We have a 12-gauge copper wire which has a diameter of 2.053 millimeters, carrying a 20-amp current. So they've given us current. They've given us the diameter of the wire, which we can calculate the area with. And they've told us that there's one free electron per copper atom. So we can figure out how many copper atoms are in this wire, also by using the density of copper that they've given us. This is a little bit involved, but it shouldn't be too bad. So the drift velocity we're going to calculate by rearranging this equation. We rearrange this equation. We know I, we know what Q is, we know what the cross-sectional area is. A equals pi r squared, where they've given us the diameter, so r is half the diameter. And then the density of copper we're going to use, and the periodic table to get our number of atoms. So we have 1 electron per atom is the number. We're going to convert this essentially. We have 6.02 times 10 to the 23rd atoms per mole. There's 1 mole per 63.5 grams for copper if you look on the periodic table. There's 1,000 grams per kilogram. We do the conversions and we get, and then there's 8.8 times 10 to the 3 kilograms per meter cubed of copper. So that's for the density of copper. And it ends up being 8.342 times 10 to the 28 electrons per meter cubed electron density in copper. So that tells you how many electrons are in a meter cubed of copper. So that's our number n. A is going to be just pi r squared. We take that diameter they give us divided by 2 squared multiplied by pi. That gives us the diameter of that, or sorry, the area of that circle with the diameter given. Then we rearrange our equation to make the drift velocity equal to current over nqa, and we multiply n, q, and a together. We have q already. We were given we were given the diameter, so we could calculate the area, and we made that conversion for the number of electrons that there are per cubic meter of copper. And in the end, you get a drift velocity of negative 4.53 times 10 to the minus 4 meters per second. Not that fast. Drift velocity is actually pretty slow. And since we're calculating this for electrons, so we put in the charge of electrons, that's why we got a negative drift velocity. That tells us that the velocity of our charges is in the opposite direction of our current. Our current was positive, our drift velocity is negative. But you notice that it's not going very fast. It's going like a tenth of a millimeter per second. 4/10 of a millimeter per second. But electricity travels near the speed of light because of this domino effect. So they don't move very fast, but the signal moves very, very fast. I want to go over again this calculation of n and what it means. If we go back to this picture, n is the number of charges in this volume that we've created, right? So n is the charge density. It's number of charges per volume. That's why when we did this, we were doing 1 electron per atom, and we were converting that to number of electrons per meter cubed. We got 8.3 times 10 to the 28 electrons per meter cubed. So n is not just any old number, it's the number per volume, or the number of charges per meter cubed. So it takes a calculation, or it's really just a conversion. But it takes a conversion like this, where you have to know the number of electrons per atom or the number of electrons per whatever, so that you can convert that to a number of charges per meter cubed. So, we've learned a little bit about circuits. We've learned a little bit about how voltage and current play their roles in a circuit. Voltage drives the current through a circuit. The current is the charge moving through the circuit in a certain amount of time. And it turns out that there is a relationship between that current and that voltage. And it was discovered and quantified by a guy named Ohm, Simon Ohm, German, Georg Simon Ohm. He was a German scientist. And you can see we're getting close to the 20th century. It's kind of amazing. Where, he's 1787 to 1854, so he was figuring this stuff out in 1800s. We're getting close. But what he discovered is that the current and the voltage are proportional. If you increase the voltage in a given circuit, the current will increase. Okay? So that was important. But the other thing that he discovered is that if you increase the resistance in a circuit, the current decreases. Well, what is resistance? We haven't really talked about what resistance is yet. If we go back to our water analogy, the resistance in a water flow is things that make the water slow down. Okay, so have you ever been to town west of here, the bridge on the west side of town, Buffalo Bill? You ever been on that bridge over there, over the river? You ever notice that in the river they have these big rock outcroppings that are obviously man-made, stuck out in the river? Why do they put those in? What's that? So it doesn't need way at the bank. That's one side effect. What they're really doing is they're slowing down the river. Okay? The river that we have going through North Platte is what's called a braided river. It's essentially a straight river that has these twisted braids and all these little islands and little things in it. And it's not a winding river. Winding rivers are like the Amazon. The Amazon is a winding river. It slows itself down because it has to turn corners all the time. Okay? Our river doesn't do that. And does our river flood a lot? Absolutely. Does the Amazon? No. The Amazon carries more water than all the rest of the rivers in the entire world combined, and it doesn't flood a lot. Because it slows itself down and prevents itself from rushing all down to the end of the river and flooding the plains. Ours floods a lot because all the water just goes super fast through Colorado. Doesn't flood in Colorado or Wyoming that much. But when it gets down here to the flat places, all of a sudden it slows down. And because it's flat, there's no hill for it to go down, and it just goes and fills it up, right? So they try to slow it down some more before it gets into town, so that it won't flood town. They prefer it to flood above town a little bit and below town rather than right in the middle of town. So they slow it down, and that's on purpose. They do that all the time in rivers, rivers like this. We have a lot of these kinds of rivers in the United States. Missouri and Mississippi are also great rivers. So you have these things that are pushing out in the middle, and they're stopping the water, and they're causing turbulence, they're causing flow to not be nice and clean, nice and straight. It's the same thing in electronics. Some metals are really good at allowing electrons to just go straight through. Silver is really great at it, copper is really good at it, gold is really good at it, aluminum is really good at it. Other metals are not so good. Nickel, tungsten, stainless steel. These metals do not allow the electrons to go straight through. They cause some turbulence, and they are more resistant. And then you put tungsten into a circuit. You have copper wire, and then you put some tungsten in the copper wire. The tungsten really slows down the current and causes a lot of heat to be dissipated. The tungsten gets really hot, in other words, as this resistance, as the electrons don't want to go through very well. But the power, the voltage is still trying to push them through it, heats up the tungsten. And then the tungsten starts to glow and you get a light bulb. The same thing goes for carbon. You can do the same thing with carbon. Carbon is a pretty good resistor in certain forms. And you can create light bulbs with carbon. In fact, the longest burning light bulb in the world right now, I believe, is a carbon resistor light bulb. It's actually in my hometown. My hometown has a lot of really weird scientific nerdy claims to fame because it's a scientific nerdy town. But let's look at the longest burning light bulb here. Longest burning light bulb is in the Livermore Fire Department. They call it by the Livermore Pleasanton Fire Department, but Pleasanton's a separate city. I don't know why they call it that. But it's been burning since 1901, and this is a field trip that all kids go on. You can actually look at the bulb cam. This is the bulb cam, 131, 2017. Yeah, so you're looking at it live right here. This is in one of the fire stations in my town. And this filament right here that's glowing, I believe is made of carbon. Let's see what it says here. Can't remember. Hey, you can buy replicas. I'm pretty sure that it's a carbon a carbon filament though. But different things, different resistors behave differently. Some of them glow, some of them just give off a lot of heat. Some of them have really interesting properties. But they're all resistors in that they slow down or they prevent the current from flowing as nicely and cleanly as it could. And they dissipate energy somehow. They take energy out of the system. Okay? That's what resistors are. In a river, it's something blocking the flow. Something that's, a big boulder in the middle of the river. Or an island in the middle of the river. Or something jutting out of the river. A big concrete or a pile of rocks or whatever else. Those are the resistors in a river. And the more of those resistors you have, the less the current is going to flow. The current is going to go down for a given voltage, for a given driving force. And eventually, he was able to combine these two ideas that he came up with. This idea, current and voltage are proportional, and current and resistance are inversely proportional. He just combined them and said, this, I think, is what's going to work. And it turned out it does work. The current is equal to the voltage divided by the resistance in many, many cases. It's not absolutely true. It doesn't work in every case, but it works in many cases. In many kind of everyday cases that we use today in particular. So here is an example of this. We have a battery and a resistor and a circuit. Right? Current is flowing from the high end of the battery. If you're not sure how to remember which end of the battery is considered the high voltage or the high potential end, the positive end of the battery, think of it this way. The small line here is a negative sign, and the big line is like a positive sign that's been turned sideways on itself. Here's the one that's supposed to be vertical, cut that off and make it a positive sign. Or the bigger end of the battery is just the bigger potential. A lot of people have a hard time remembering which side is which. The longer line is the bigger side, or the positive side. Anyway, so the current is flowing from the positive or through the resistor around to the negative side. It's going around and around the circuit. And the current that is being pushed through this resistor is dependent on the voltage directly. So if you increase the voltage, you can get more current. But it's inversely dependent on the resistance. So if you increase the resistance, the current will go down if the voltage stays the same. If you decrease the resistance, the current will go up if the voltage stays the same. So using Ohm's law to calculate things, you can rearrange it into three different forms. You can calculate for I equals V over R, I current equals voltage divided by resistance. You can calculate R to be voltage over current, or you can calculate current to be voltage equals current times resistance. So V equals IR. You can have three different versions of this equation and calculate something. In this case, they want us to calculate the resistance of a headlight if it has 12 volts across it, 12 volts of potential across the light bulb, and, 2.5 amps through the light bulb. This is an important point right now. When you're talking about potential, you talk about potential between 2 points, or you can say the potential across something, which means on one side of it compared to the other side. Potential or voltage is always between 2 points. It's not something that goes through the circuit. Current is always measured, is always talked about as current through something. So in this case, the current is going through the bulb. We're measuring the potential on either side of the bulb. The potential difference across the bulb, in other words. So it'll be 12 volts divided by 2.5 amps. In this configuration of the equation, we get 4.8 ohms for that resistor, and that's pretty normal. Most resistors that are light bulbs, that end up being light bulbs, are not a very high resistance. 4.8 ohms is pretty low resistance. The interesting thing about resistance is that as wires get hot, their resistance increases. So the resistance of that bulb will get higher and higher as it gets hotter and hotter. And when it's cold, the resistance is actually much lower. For copper, the resistance is almost zero. Copper's resistance is extremely low. That's why it's such a good conductor, a good wire. The same is true of silver and aluminum. Their resistances are like 10 to the minus something ohms. And you want a very low resistance for your wires because you don't want them to heat up. So here's a demonstration of what I meant by voltages measured across something. There is a device called a voltmeter, which we will see and we will study a little bit more. But a voltmeter measures the potential difference between 2 points in a circuit. And if you want to know the voltage across a light bulb or a resistor, you connect the voltmeter on one side of the resistor and on the other side of the resistor. That's how you actually measure the voltage in a circuit. We often call that the voltage drop across a resistor, or the potential difference or potential across a resistor.
I have a quick question.
Yes.
For Ohm's law, up top it says 1 omega over 1 ohm equals 1 V over A. So can your A and R be interchangeable? Or are they the same thing? So I thought A was for an
No, sorry, I should have explained what they're talking about here. This is not part of Ohm's law. This is just demonstrating what the units are for ohms. So they use Ohm's law to calculate this because if you rearrange this so that it's R equals volts over amps, then you get the same equation. But what they're doing is they're just showing what the units of ohms are. So the units for resistance, which we call ohms, are volts per amp. That's just the units.
So 1 resistor equals per amp.
Yeah, so if you have 1 ohm of resistance, that's what this thing right here means, ohms.
So that's how you would refer to
If you have a 1 ohm resistor, that resistor allows 1 amp to flow for every volt voltage you put across it. So yeah. So that's Ohm's law, and you're going to do a fair amount with Ohm's law over the next little while. Okay, so you remember when we were talking about capacitors and how capacitors, how it's the amount of area that you have on a capacitor that determines how much charge it can hold. So the capacitance is directly affected by the area of the plate that's holding the charge of the capacitor, right? Well, with a resistor, it's not about area. It's about length of the resistor. And the longer a resistor gets, the longer the distance is that the charge has to try to get through that resistor. Remember that resistors are like things that prevent flow from flowing. And so if you have a longer resistor, it's going to prevent the flow longer as the charge tries to get through it. So longer resistors made of a particular material are bigger resistors. They cause more resistance. But if you make the resistor bigger around, it's like opening up the river. Even though it is a resistor, if you make it bigger around, if the cross-sectional area is bigger, it makes the resistance smaller. And so we have this relationship between resistance and the geometry of the resistor. Resistance of a resistor is directly proportional to the length of the resistor, so the resistance gets bigger if the resistor gets longer, but inversely proportional to the area, so if the area gets bigger, the resistance gets lower. And then you have to put in this thing that we call resistivity that is dependent completely on what the material is made of, what the resistor is made of, what material it is. So every material that you can make resistors of has a resistivity, which we call rho, and we have a table for those resistivities down here. And you can start to see now why certain things make great conductors and certain things make great resistors. Silver makes a great conductor. Its resistivity is 10 to the minus 8. It's very, very small. A resistor made with silver has almost no resistance. Same thing with copper, gold, and aluminum. They all have very, very low resistivities. 2.65 times 10 to the minus 8. Then you get into other things that start to have more resistivity. It's still 10 to the minus 8, but notice that it's twice as much as aluminum. Right? 5.6 times 10 to the minus 8. Iron, twice as much as tungsten. Platinum, same as iron. Steel, twice as much as platinum. Lead, same as steel. These things start to have much more resistivity until they get to be 100 times more and even like 10,000 times more. Carbon is a great resistor. In fact, most resistors that you find in electronics are made of carbon because it's such a great resistor. Germanium, way more resistance. Till you get up into silicon, which has a resistance of resistivity of 2300. Silicon almost stops current. In fact, it does stop current at certain voltages as long as you keep the voltage low. If the voltage is like at 1 or 2 volts and you try to drive current through silicon, it will literally just stop it. Current can't go through silicon. Silicon is kind of like glass, in case you're wondering what it looks like. It kind of looks like a glass that you can't see through. It's shiny, and when you break it, it breaks like glass, and it has sharp edges, but it's kind of gray, silverish, and you can't really see through it at all. But that's the resistivity of silicon is extremely high compared to the resistivity of these other metals. And silicon isn't a metal. Silicon is what we call a semiconductor. Then you get into insulators. The resistivity of insulators is extremely high. 10 to the 14 for amber. Glass, 10 to the 9 to 10 to the 14, depending on the kind of glass. Mica, quartz, rubber, all these things, sulfur, really, really high resistivities. They're going to just stop current unless you drive unless you put a huge voltage across them. Can electricity go through rubber? Yes, but it has to be at a very high voltage, extremely high voltage. That's why rubber is often used as an insulator for tools, for electricians to use. Keeps them safe. Fiberglass is used because fiberglass ladders, fiberglass tools are used by electricians because it prevents the current from flowing through their tools. It's an extremely good resistor, has this extremely high resistivity. And if you want to actually calculate the resistance of a resistor, what do you need to know? You need to know the resistivity of the material, so you need to look on that table or look it up on Google. You need to know how long the material is in the direction that the current's going to flow, and you need to know the cross-sectional area of the material. So, how do we do this? Here they're actually going to calculate the cross-sectional area because they've been given everything else. They've been given the resistivity, the length, and the resistance. So we have a resistance of 0.35 ohms, a cylinder that's 4 centimeters long, and we want to know the diameter of this thing. So we calculate, we're going to rearrange this to calculate the area and use the area to calculate the diameter. We plug in our resistivity for carbon, the length that they've given us, and divide by the resistance they've given us, and we get an area of 6.4 times 10 to the minus 9 meters squared. We know that that area has to equal pi times the diameter squared divided by 4. Why do we know that? Because, let me show you really quick. What's my Creations? So what the area for a circle is equal to pi r squared, right? But we don't have r. We're not looking for r. We don't have r. We have diameter, right? They've given us diameter, so diameter is r is diameter divided by 2, so it's pi times diameter divided by 2 squared. If we square this out, we get pi d squared over 4. We want to know what the diameter is. So we solve for the diameter. The diameter squared equals area times 4 divided by pi. Right? And then we take the square root of both sides. And if we go back to where we were, that's what we see here. Pi times diameter squared over 4. Solve for the diameter. You get that 4 is in there. The pi is switched around. But anyway, they're solving for that, and they get 2a over p to the 1/2. And that's what we would get. So we end up taking the area divided by the how do I use p? It should be pi. That should be pi, not p. Area divided by pi, I take the square root of it. And they took the square root of 4 and got the 2 already. And then they go ahead and calculate that out to get 9 times 10 to the minus 5 meters for diameter, 1/10 of a millimeter.
Rho is the number we would get from the table, it's not a constant.
Yeah, rho is something you get from the table, depends on the material. So every material has a different resistivity. But there's one other thing. Temperature affects resistivity in materials. And so you actually have to take that into account sometimes too. If you're pumping current through a metal, you're probably going to change its temperature. So its resistivity will change. Or maybe it's a different temperature because you're using it in Antarctica or you're using it in Brazil. And so the temperatures start out less or more or whatever else. So maybe you need to calculate a new resistivity, in which case you use this equation right here. The new resistivity, which would be rho, would be equal to the initial resistivity from the table, P0, rho 0 rather, times 1 plus alpha delta T, where alpha is the temperature coefficient of resistivity, which you get from another table. And every conductor has its own alpha, right? So it just gets more and more complicated. Some materials change their resistivity a lot when the temperature changes. Some of them change it a little. Just depends. And you might choose your material for that reason. You may want something that changes a lot when it gets hotter. You may want something that just changes a little or changes hardly at all.
What's the standard temperature?
Standard temperature is, I believe it's 0. Let's see here. In some situations, standard temperature is 0. In some, it's 25, and that's in Celsius. I think it's 0. I think they calculate all these at 0. I don't think it'll matter at all to you because this equation only uses a difference in temperature. So an example where a resistor that changes temperature is a good thing is if you're using it to calculate, if you're using it to measure temperature, for example. Right? So these thermometers that have the little digital readouts are actually resistors. And what they do is the resistor has a current flowing through it from a battery inside the resistor, inside the thermometer. And then they put that resistor in your mouth. The resistor is in the tip of the thermometer or wherever, put it in your ear, whatever they do. And then as the resistor changes temperature to match the temperature of your body, then the amount of current flowing through it is going to change. As it warms up, the resistance will increase, and so the current will go down. And they know because they know what the resistor is made of. They know how much it will go down for different temperatures. So they can measure your temperature that way. The one that they put in your ear is actually not a resistance temperature. It's actually an infrared one. So that one is not true. But this is how temperatures are taken for just about anything anymore. When when the heater kicks on, the temperature device that is used to measure temperature is actually what's called a thermistor, which is a thermal resistor. It's a resistor that changes its resistance with temperature. And many other situations as well. In your car, everything that's measuring temperature in your car is measured with thermistors or thermal resistors. So here's an example where we're going to change the resistivity of a material in temperature. Now, the first equation that they gave us was this one where the resistivity changes, but you can actually also use that just for resistance. You can use the same equation for the original resistance of a resistor and the final resistance after it's changed its temperature. So here we're going to use that second equation. We have a filament that has an original resistance of whatever it is. We don't know what it is. Oh yeah, it is. It's 0.350 ohms given somewhere. Anyway, tungsten. Where does it say that it changes? No, the original. Anyway, they tell us the original is right here. And the temperature change is going to be 2850. It's going to go from 20 to 2850. So the change will be the 2850 minus 20, and you get a delta T of 2830 centigrade. So 2830 degrees Celsius. So we know delta T, we know the original resistance. We just have to look up alpha for this type of resistor. This is tungsten, so we go up and look alpha for tungsten. Turns out to be 4.5 times 10 to the minus 3. Plug in the stuff, we get a 4.8 ohm resistance. Finally, the original resistance being 0.35. You can see that it went up by more than a factor of 10. So tungsten changes its resistance quite a bit when it heats up. And that's why it starts to glow, because it starts to really dissipate energy, it starts to glow, and it makes a good headlight, or a good lantern in general.
It always has to be in Celsius.
Yes, it should be in Celsius. Or Kelvin, either way. Thanks. Okay, we will save the last 4 sections for next time. These two are kind of related, and the last 2 are kind of related. So we will stop there. I will put together a homework assignment for you guys for this. And we will... Chapter 19 was actually due... Let's see here. Chapter 19 was due the 30th. Why is it's due the 31st? Did I change that? I must have. So that's today, right? I don't know. Let's go look. Apparently it's due the 31st, which is today.
It's due like almost 12 hours ago.
Oh, yes. So it was due yesterday. Can't remember. Originally, I had it due at a different day, and then I changed it. I don't remember what my original one was. It doesn't keep track of that. What's that?
I was saying I didn't connect it.
Oh. Well, if you need an extension for a reasonable amount of time and a reasonable number of questions, send me an email. Any other issues or concerns, send me an email, of course. It's always easiest to send me an email because then I can fix things and remember to fix things. But the next homework assignment, I'm going to try to have homework assignments due before the weekend. And the reason is because I don't want you to wait until after the weekend, because then you've not seen the material for almost a week. So I want you to get working on it right away, and I will make this homework assignment and have it available for you within the hour for this chapter, and we will finish it Thursday so that you might have questions. But you really should work on this homework assignment Tuesday and Wednesday, have questions for me Thursday, and then work on the rest of it Thursday and Friday and have questions for me on Friday if you have any before the weekend. And I don't mind having it due like Saturday, but I don't want to do Monday very often or Tuesday, because then you're just kind of doing all the homework on one day. It just has a tendency to be that way. So the latest I will do assignments from this point forward is probably Saturday evenings. But getting help on a Saturday is much less easy than getting help on a Friday or a Thursday, just because I'm going to be busy for Saturdays. I won't be always at my students' beck and call. So I try to check my email probably 2 or 3 times on Saturday, but it's not always very constant. So anyway, we will end at this point. Have a good day. I will be around for the next hour, 2 hours or so. If you need me for anything.